Have you ever stopped, really paused to think about how we know what we know? Or maybe how we figure out what information is actually trustworthy in this, well, flood of data we live in? Today, we're going deep. We're looking at the architecture, the very bones of how solid knowledge gets built.
That's exactly it. We're diving into research methodology. Now, our guide is this concise handout, originally for PhD students, but honestly, don't let that put you off.
Right.
It's not just for academics. Think of it more like a universal toolkit for anyone, really, who wants to be properly well-informed. It's a kind of shortcut to understanding how credible information is actually put together.
Yeah, and our goal here is to pull out the really important stuff, the key nuggets, to give you a clearer picture of how reliable knowledge is built, from the ground up. We think there'll be some real aha moments, maybe some surprising bits too, because this isn't just theory, is it?
Not at all.
Whether you're prepping for a big meeting, trying to get a handle on a new field, or maybe you're just super curious about how we get to knowing things. This deep dive should help you critically look at pretty much any information that comes your way. Okay, so let's start right at the beginning with this idea of scientific inquiry. It's more than just asking questions, isn't it? It's a whole process.
Well, absolutely. It's a very disciplined, systematic way of exploring things. Collecting evidence, proper evidence, and then reaching conclusions that are actually backed up. The main goal is generating knowledge you can rely on, knowledge that's transparent. Others can see how you got there, and ideally replicable and meticulously recorded. You need that clear audit trail. And it's iterative. That's key. You refine your questions, you gather data, you interpret what you find, and that often sends you right back to refining the questions again. It's a cycle.
It's fascinating how deep the philosophical roots go here. Before we even ask how we know something, we kind of have to wrestle with what actually exists to be known.
Which brings us to ontology, right? Precisely. Ontology. It's the philosophical study of what is real, fundamentally, what exists. It's like the basic map of reality that shapes how we even structure our data. Think about, say, Google. Search engines use data ontology to get that Paris isn't just a word, it's a city, with demographics, history, districts all connected.
Okay.
Or in drug development, huge data sets, proteins, genes, diseases. They're organized based on how they actually relate to each other in reality. Ontology defines those basic things and relationships we're trying to study.
So ontology is the map of what's real. Then epistemology. That's about how we read the map, how we get knowledge.
Exactly. Epistemology is the theory of knowledge itself. How do we acquire it? What are its sources? And, crucially, a researcher's perspective on this, it massively influences how they interpret data. That's why stating your epistemological stance is so important in research. We can broadly think of knowledge as either empirical stuff you can objectively describe, observe, prove, or intuitive, which is more about beliefs, maybe faith.
And these philosophical views directly lead to different research approaches. There's this big split, isn't there? Positivism versus interpretivism.
That's the main divide, yeah. Positivism comes more from the natural sciences. It aims for objectivity. It tends to use statistical data, often from large groups, testing hypotheses, aiming for objective interpretation to find general laws. It fits really well with quantitative methods.
Nice numbers.
Exactly. Interpretivism, though, it sort of grew in response, especially in social sciences. It acknowledges that the researcher is part of the process, an active interpreter. You're never totally objective. So interpretivists focus more on specific situations, specific contexts. They accept that reality and our knowledge of it can be subjective, shaped by experience. It gives you incredibly rich understanding, but it's usually less generalizable.
Okay, so let me see if I've got this straight. Your ontology, what you think is real, shapes your epistemology, how you think you can know about it. And that then tells you which methods to use.
You've got it. A positivist believing in one objective reality. They'll naturally lean towards quantitative methods, big samples, stats, looking for universal laws. An interpretivist, seeing reality as perhaps socially constructed. They'll likely choose qualitative methods, in-depth interviews, thematic analysis to get at those nuanced experiences. And if you try to mix them inappropriately, say using in-depth interviews, but trying to force them into purely objective, generalizable laws, the research just becomes incoherent. It doesn't hang together.
That makes sense.
Okay.
Okay, let's shift from the big philosophical ideas to the actual building blocks, the nuts and bolts of research. We often talk about these abstract things, right? Concepts we can't quite
Exactly. Those are our constructs, abstract concepts. Things like intelligence, motivation, self-esteem, stress levels. You can't directly measure them with a ruler or a scale. Their presence, their strength, we have to infer it from other things we can observe variables. So defining constructs clearly is step one. Step two is operationalizing them.
Operationalizing.
Yeah, developing concrete ways to measure them, using specific indicators, turning the abstract idea into something measurable.
Okay, so constructs are abstract, and then we have variables. These are the things we can measure directly, things that change or vary.
Precisely. Age, height, an actual IQ test score, a score on an anxiety scale like the G87, they're much less abstract. You can assign a specific value or category to them.
And understanding how these variables interact is where it gets really interesting, you said.
Definitely. The basic setup is the independent variable, or IV. That's the presumed cause. Often it's what the researcher changes or manipulates. Then there's the dependent variable, the DV. That's the presumed effect, the outcome you measure. But the simple IV causes DV story is often too simple. That's where mediating variables come in. Mediators explain how or why the IV affects the DV. They're the intermediary step. For example, maybe sleep quality improves academic achievement, DV. How? Well, perhaps through better alertness, the mediator. Sleep improves alertness, and alertness improves achievement.
Oh, okay, so it's the pathway.
It's the pathway, exactly. Or maybe salary influences spending on health screenings, DV. The mediator might be education. Higher salary might correlate with higher education, and higher education leads to more health awareness and screening. The theory is that the IV causes the mediator, and the mediator then causes the DV. Sometimes if the mediation is really strong, the direct IV-DV link might even vanish when you account for the mediator.
Interesting. And then there were moderators.
Right, moderating variables. Moderators don't explain the how. They influence the strength or the direction of the relationship between the IV and DV. They tell us for whom or when or under what conditions the relationship holds. Like maybe social media use is linked to loneliness, DV, but age is a moderator. The link might be much stronger for teenagers than for older adults.
Okay, so it changes the relationship itself.
Changes the relationship. Or age could moderate the salary and health screening, DV link. Maybe the connection is stronger for older people. Moderators are often pre-existing characteristics, unlike mediators, which are usually affected by the IV.
So let's bring this back to the listener. Why does understanding mediators and moderators matter for you? It means we can get beyond simplistic explanations, right? Like exercise reduces stress. That's just IVDV.
But with mediation, it could be exercise reduces stress because it boosts endorphin levels. That's the how.
And moderation might be exercise reduces stress, but the effect is much stronger for people who started with moderate stress levels. That's the when or for whom.
Exactly. If you ignore these, you risk oversimplifying or drawing flat-out wrong conclusions, whether you're reading a research paper or just, figuring out why something is happening in your own life or work. And it highlights why knowing if something is a construct, like stress, versus a variable, like a score on a stress questionnaire, matters. They play different roles in building that nuanced explanation.
Okay, got it. So with those building blocks clear, what about the overall research process? You mentioned 7 steps.
Right, the 7-step research process. It's a roadmap, really, and remember, it's iterative. Step 1, identify the research problem. Is it significant, clear, doable, new, measurable, relevant, interesting, ethical? Lots to consider there. Step 2, literature review. See what's already known, find the gaps. Step 3, formulate objectives and hypotheses. And they need to be smart.
Tomorrow.
Specific, measurable, achievable, relevant, and time-bound. Really clear goals. Step 4, design your methodology. How will you actually do the study? Step 5, collect your data. Step 6, analyze the data. And Step 7, report your findings. Disseminate what you learned.
And you stressed that iterative part, repeat steps 2-7. That really stood out. It's not just a straight line.
Absolutely not. Flexibility is key. You do a lit review, you formulate an idea, maybe you try to collect some pilot data, and bam, you hit a snag. Or you find something unexpected that forces you to maybe go back, rethink your question, adjust your methodology. It's constant refinement. So what looks like failure data not fitting, for instance, is actually vital feedback, an opportunity to improve the research.
Which leads nicely into choosing a topic. How do you land on something good?
Well, several things matter. Relevance and significance are huge. Does it actually contribute something meaningful to the field, maybe to solving a real-world problem, informing policy? Then, originality. You need to find a genuine research gap, something that isn't already well understood. And critically, feasibility. Do you have the time, the money, the skills, access to the data you need? If you're a student, does it align with your supervisor's expertise?
Makes sense.
Personal passion helps too, of course. Clarity of the concepts involved, how it fits your career goals, lots of factors.
You mentioned interdisciplinary research as being important for finding gaps.
Increasingly so, yes. Tackling complex problems often requires combining insights from different fields. Think about environmental sustainability. You need the ecology, the climate science from STEM, but you also need the economics, the policy analysis, the sociology from the social sciences to understand human behavior and governance. Climate change, conservation, urban planning, they're all deeply interdisciplinary. It often requires what people call a T-shaped skill set, deep knowledge in one area, but broad understanding across others.
So how do you actually find those gaps beyond just searching keywords?
Good question. An exhaustive review is the baseline, really reading deeply. And definitely look at those suggestions for future research sections and papers. Researchers often point out gaps themselves. But you can go further. Thematic analysis of the literature, looking for themes that are missing, or maybe where findings contradict each other, looking at historical trends. How have the key questions or methods in a field changed over time? Where are they heading? And then there are tools for citation mapping, visualizing how papers connect to each other. This can reveal pockets of research that aren't talking to each other, revealing really interesting gaps, often at the intersection of disciplines.
Once you have a potential gap, formulating the actual research problem is key, you said.
Yeah. Absolutely critical for focus. Your objectives state precisely what the study aims to achieve, SMART objectives, remember. Your research questions narrow down the inquiry, and if appropriate, hypotheses offer testable predictions. A common mistake is being too vague. To study the impact of technology on society, what technology? What impact? Which part of society?
Right, it's huge.
Exactly. A much better, refined example. To assess the impact of social media use on the mental well-being of adolescents, age 13-18, in urban areas of country X, as measured by self-reported anxiety and depression scores over a 12-month period. See, specific, measurable, achievable, relevant, time-bound.
Much clearer. And this idea of significance and relevance, why should you, the listener, care about this part?
Because good research has impact beyond just academia. Theoretical implications, does it change how we understand a concept? Practical implications, can it be used to solve a real problem, improve a process? Policy implications, can it guide government decisions? And broader societal implications, does it raise ethical issues or affect how we live together? Showing how your findings connect to these wider concerns, like informing policy or tackling societal challenges, really demonstrates the value and maturity of the research.
Okay, so we have a problem, we understand its significance. Now, the blueprint,
Yeah.
the research plan, you called it a dynamic contract.
Yeah, it's a detailed roadmap. Objectives, methods, timeline, resources. It keeps you on track, helps you anticipate problems. It's dynamic because, as we said, things might need to change, but you need that initial structure. It's a critical risk management tool, really.
And a huge part of that plan is choosing the core research design. You mentioned the big split, qualitative and quantitative.
Right. Qualitative is about depth, understanding the why and how. Using non-numerical data, interviews, observations, journals, you typically build theories from the data. Smaller samples, often not random. Great for flexibility, rich insights. Downsides. Can be subjective, harder to generalize. Quantitative is about measurement, testing theories, the what, how many, how often. Uses numerical data surveys, experiments. You test theories with data, usually larger random samples. Strengths are objectivity, generalizability, limitations. Might miss context, controlled settings aren't always like real life.
And you mentioned mixed methods is getting more popular.
Definitely. Using both qualitative and quantitative strategically in one study. It lets you leverage the strengths of both, maybe triangulate findings, check if different methods point to the same conclusion, gives you a much more complete picture.
The choice depends entirely on the research question.
Yes. It's a strategic decision. What do you need to find out? Deep understanding or broad pattern?
Then there were application-based designs, pure versus applied.
Exactly. Pure research is curiosity-driven, expanding fundamental knowledge. No immediate practical goal in mind. Think theoretical physics, exploring basic biological processes. It lays the foundation. Applied research is focused on solving specific, practical problems, developing a new drug, figuring out why sales are down, improving a teaching method. Tangible solutions, but they feed each other. Pure research often leads to breakthroughs that enable applied research later. And applied research often reveals gaps where we need more fundamental, pure understanding. It's a cycle.
Okay. What about descriptive studies? You mentioned time was important.
Yes, the temporal dimension. Cross-sectional studies are like a snapshot. Data from lots of people, but at just one point in time. Great for measuring prevalence, how common is something right now, like a census. They're relatively quick and cheap, but, and this is crucial, they cannot definitively prove cause and effect. You see correlations maybe, but you don't know which came first or if something else caused both.
Right, the snapshot limitation.
Exactly. Contrast that with longitudinal studies. You collect data from the same group of people repeatedly over time. Weeks, months, years, even decades. This lets you track changes, see how things evolve. It gives you much stronger evidence for cause and effect. Following smokers versus non-smokers over 20 years to see who develops cancer that's longitudinal?
But they must be challenging to run.
Oh, very. Time-consuming, expensive, and keeping track of the same people for years. Participant dropout is a major issue.
So cross-sectional gives you breadth quickly, longitudinal gives you depth and stronger causal hints over time, but it's harder.
That's a good summary. And researchers using cross-sectional data must be careful not to claim causation when they can't prove it.
Now, for studies really focused on cause and effect, experimental studies, you talked about field versus lab.
Right. Field experiments happen out in the real world, in natural settings. You still manipulate something, the IV, and randomly assign participants, but it's within their everyday environment. Think testing different versions of an online ad or studying how different types of community policing affect crime rates. Great for relevance, for seeing how things work in practice. Challenges include controlling all the other noise in the real world, and sometimes ethical considerations like informed consent if people don't know they're in a study.
Okay, real world, but with some control. And laboratory experiments.
Those are in highly controlled environments, like a university lab, a medical testing facility. Here, you can maximize control over extraneous factors, isolate the IV's effect on the DV much more precisely. Fantastic for high internal validity, being really confident that your IV caused the change in your DV. Think testing a new drug under controlled conditions or measuring brain activity during a specific task. The downside, the artificial setting might limit how well the findings generalize to the real world that's external validity. Plus, you often have smaller samples, and people might act differently just because they know they're being watched, the Hawthorne effect.
So it's a trade-off again. Lab gives you tight control, high internal validity, but maybe lower real-world applicability. Field gives you more realism, better external validity, but less control.
Exactly. And your research question dictates which trade-off is more acceptable. Do you need absolute proof of causality, or do you need to know if it works in the messy real world?
You also briefly mentioned some other designs, exploratory, case studies, focus groups.
Yeah, those are often crucial early on. Exploratory research is for when you know very little about a topic. It's flexible, often qualitative, helps you generate initial ideas or hypotheses. Case studies involve an incredibly deep dive into one specific instance, a person, a group, an organization, an event. Great for understanding complexity, developing theories, rich data, but obviously limited generalizability from just one case. And focus groups bring together a small group for a moderated discussion. Excellent for exploring opinions, attitudes, motivations. Again, rich qualitative data, but watch out for groupthink, where people conform, and you can't generalize easily from one or two groups. Often these designs lay the groundwork, generating insights that you might then test more rigorously using quantitative methods later.
Okay, let's try that tech company example again. They want to know why users ditch their app and how many are doing it. How would you combine these ideas?
Right. A mixed methods, sequential explanatory design would be perfect. Phase 1. Quantitative. Analyze their existing app usage data, look at abandonment rates over time, longitudinal tracking, and maybe survey current users. Cross-sectional. This tells you the what and how much, where are people dropping off, how many. Phase 2. Qualitative. Based on the quantitative findings, maybe lots of people drop off at the payment screen. You then conduct focus groups or in-depth interviews with users who did abandon. Ask them why. Was it confusing? Too expensive? Technical glitches? This gets you the deep understanding. You then integrate the findings. The qualitative stories explain the quantitative patterns. That gives the company really actionable insights to improve the app.
That makes perfect sense. Combining the numbers with the stories. Okay, so we've designed the study. Now the tool's actually gathering data. Questionnaires seem common.
Very common. And questionnaire design is an art and a science. It's iterative. Define your goals. Draft questions, keep them short, direct, simple. Avoid jargon, avoid double-barreled questions asking two things at once. Avoid negatives as possible, they confuse people. Avoid leading questions that suggest an answer. Then, absolutely critical, pilot testing. Try it out on a small group similar to your target audience. Does it make sense? Are the questions clear? How long does it take? Does it seem reliable? Valid. You catch problems before the main study. It's quality control. Then revise and finalize.
And there are different types of questions you can use.
Definitely. Open-ended questions let people answer in their own words. Great for rich why insights, but harder to analyze quantitatively. Close-ended questions give fixed options. Yes, no, multiple choice, rating scales. Easy to analyze, quick to answer, but might miss nuance. Disguised questions are indirect, often used for sensitive topics like asking about socially desirable behaviors where a direct question might not get an honest answer. And skip questions or skip logic are really useful. Based on an answer, they direct the respondent to the next relevant question, skipping irrelevant ones. Improves the experience, reduces frustration and dropout.
So choosing the right mix and order is key.
Crucial for good data and keeping people engaged.
Then you mentioned measurement scales. This seemed really important for the stats later.
Fundamental. The scale type dictates what math you can do. Nominal scale. Just categories, labels, gender, favorite color. No order. You can only count frequencies. Ordinal scale. Categories with a meaningful order, but the gaps between them aren't necessarily equal, like low, medium, high satisfaction, or educational levels, high school, bachelor's, master's. You can find the median or mode, but not really the average.
Okay.
Interval scale. Ordered categories with equal intervals between them, but no true zero. Temperature in Celsius or Fahrenheit is the classic. 0 degrees doesn't mean no temperature. IQ scores are another. You can calculate mean, standard deviation, correlations. Ratio scale, the highest level. Ordered, equal intervals, and a true 0 point, meaning 0 represents the complete absence of the thing being measured. Weight, height, income, age. Here you can do all arithmetic averages, ratios, proportions.
You really have to know what kind of scale your data is on before you analyze it. You can't calculate an average satisfaction score if you only measured it as low, medium, high.
Exactly. It limits your analysis and the conclusions you can draw. Are you sure your data can answer the questions you're asking of it? That's a key check.
And within those scales, different ways to get responses, like Kurzert scales.
Right, scale response formats. The Likert scale is super common for attitudes. Strongly disagree to strongly agree, usually 5 or 7 points. Converts opinions into structured data. A graphic scale uses a visual line or bar, maybe with numbers or descriptions at points. Can be intuitive. A semantic differential scale uses pairs of opposite adjectives like good, bad, fast, slow, modern, traditional. Captures nuances and perception well. The format influences the kind of data you get.
Now, this next bit seems critical. Reliability and validity. You said reliability is consistency.
Yes. Does your measure produce consistent results under consistent conditions? Cronbach's alpha is a common way to check internal consistency. Do the different items on your scale seem to be measuring the same underlying thing? It ranges from 0 to 1. Generally, above 0.7 is acceptable, above 0.8 is good, above 0.9 is excellent. But interestingly, if it's too high, like above 0.95, it might mean your questions are basically asking the exact same thing redundant. You might be able to shorten your scale.
Okay, so reliability is consistency. What about validity?
Accuracy.
Exactly. Validity is about, does your measure actually assess what it's supposed to assess? And this is the killer point. A measure can be reliable, but not valid.
The broken scale example. Always reads 150 pounds, reliable, but you actually weigh 170, invalid. Precisely. It consistently measures the wrong thing. So, validity is paramount. Content validity asks if your measure covers all the important aspects of the construct, often judged by experts, refined through pilot testing. Construct validity is about how well the measure fits with the underlying theory. Especially important for abstract things like happiness. Does it correlate with things it should correlate with, convergent validity? And does it not correlate with things it shouldn't correlate with, discriminant validity?
Neglecting validity just ruins the research, doesn't it?
Fundamentally, it's an ethical issue too. You're potentially drawing wrong conclusions.
So, back to Cronbach's alpha. If your job satisfaction scale gets 0.62,
questionable. You'd need to revise those questions.
but if academic motivation gets 0.95,
Excellent internal consistency, but yeah, check for redundancy. Maybe you can make the questionnaire shorter and still capture the construct well.
and that customer satisfaction example for the coffee shop, you'd mix question types, use skip logic, maybe Likert for overall satisfaction, and definitely pilot test it all first.
Absolutely. Pilot testing is non-negotiable for quality.
Okay, final section. Getting data from the right people, sampling, and then the software to handle it.
Yeah.
Population versus sample.
Right. The population is the entire group you care about. All university students in the UK, maybe. The sample is the subset you actually collect data from. The goal is for the sample to be representative of the population. If it is, you can generalize findings from the sample back to the whole population. If the sample is biased, say, you only surveyed students from wealthy backgrounds, your conclusions about all students would be invalid. It's a major threat to external validity.
So how do you get a representative sample? different techniques?
Several main sampling techniques. Simple, random sampling. Everyone in the population has an equal chance of being picked. Purest form minimizes bias. But you need a complete list of everyone, which is often impossible for large populations. Stratified sampling. Divide the population into relevant subgroups, strata, like different departments in a university, then randomly sample from each subgroup, ensures representation of all groups. More complex. Systematic sampling. Pick people at regular intervals from a list like every 10th person. Simpler than random sampling often works well, but risk of bias if there's a hidden pattern in the list that matches your interval. Multi-stage sampling, used for large, spread-out populations. You sample in stages, e.g., randomly select regions, then randomly select cities within those regions, then randomly select neighborhoods, then households. Efficient but complex design and analysis.
Choosing the right one depends on the situation.
Always. It's a strategic choice based on your question, your population, your resources, and you need to justify your choice and understand its limitations.
Where did the data actually come from? Primary versus secondary?
Primary data is data you collect yourself, specifically for your study. Surveys you run, interviews you conduct, experiments you perform. You control the process, tailor it to your needs. But it takes time and money. Secondary data is data someone else already collected. Government census data, existing research databases, company records, published statistics can be incredibly useful, time-saving, cost-effective, access to huge data sets. The drawback: you're stuck with the variables they collected, and you might not know the quality of the original data collection.
So use secondary if it fits, but be ready to collect primary for specific.
That's often the best approach. Leverage what's out there, but fill the gaps with your own targeted data collection if needed.
How do you know how many people you need in your sample? Sample size estimation.
Crucial for having enough statistical power to detect effects and for precision. You need to think about your desired confidence interval, how sure you want to be that the true population value falls within your estimated range, often 95%. And your acceptable margin of error, how much uncertainty you can tolerate in the result, e.g. plus or minus 3%.
And you gave examples. Estimating AI tool use needed over 1,000 students.
Right. For 3% margin of error at 95% confidence, assuming about 40% use AI, and estimating PhD graduate income within $1,000 margin of error, with 95% confidence, assuming a standard deviation of $10,000, needed around 385 graduates. You use specific formulas, always round up, and factor in that not everyone you ask will respond.
Okay. And finally, the software tools to actually crunch the numbers or analyze the text.
Essential these days, SPSS is very popular in social sciences, quite user-friendly for quantitative analysis, frequencies, regressions, etc. Excel is great for basic stuff, organizing data, simple charts, pivot tables, but limited for complex stats or huge data sets. R is a free open-source programming language, immensely powerful, can do almost any statistical analysis imaginable, great for complex modeling and visualization, but it has a steeper learning curve. It's code-based. And for qualitative data, interview transcripts, field notes, videos, NVivo is a leading package. Helps you organize code, find themes, manage mixed methods data.
So learning at least some of these is pretty much required now for serious research.
Increasingly so, yes. Proficiency with these tools is expected for doing robust empirical work. They're the workbench where knowledge gets built from the data.
Wow. Okay, that was quite the journey. From the deep philosophy of what's real and how we know it, through constructs, variables, the whole research process, designing studies, measuring things carefully, right down to sampling and the software.
Covers a lot of ground. But understanding these fundamentals, it's not just for academics writing dissertations. For you listening, it really is about becoming a much more critical consumer of information. When you see a study, or even just a news report citing a study, you can start asking better questions. What was their methodology? Was it appropriate for the question? How did they measure that concept? Who was in their sample? Could there be alternative explanations? It helps you see the strengths, but also the crucial limitations.
It's about moving beyond just accepting findings at face value.
Exactly. It's about understanding the process, the potential pitfalls, and discerning what knowledge is genuinely reliable in this absolute ocean of data we swim in every day. It helps you build your own informed perspective rather than just taking someone else's word for it.
So here's a final thought for you to mull over. In this age of information overload, how can really grasping this architecture of knowledge empower you? Not just to consume information, but to truly understand where it comes from, how it was built, and critically evaluate its limitations before you decide what to believe or how to act. Until next time, keep diving deep.